golf balls are one of the earliest modern examples of a super effective aerodynamic flow control device, dimples. For golf balls, dimples are used to make the ball behave far more predictably than if the ball was smooth. The reason why they do that is because if you have a completely smooth surface, then the flow over the ball is very unsteady. It doesn't have that much energy, so at one point in time, the flow on one side will separate, while the other side will remain attached. And then that causes an imbalance in the pressures, which then moves the ball to one side. Then in the next instance in time, the exact opposite happens. That makes the ball effectively perform like a knuckleball in baseball, where it just moves around suddenly through the air and you can't really predict what's going to happen. And even if you spin the ball really fast, it doesn't really do that much either because the surface is so smooth that there's nothing there to really bite into the flow and turn it up. So there's nothing really to grip onto in a way. That's where adding dimples comes into it. For a golf ball, the dimples roughen the surface and makes the flow more chaotic, but in a controlled fashion. That allows the flow to stay attached for a longer time over the ball and in a much more steady way. So the ball will now behave consistently, and there'll be forces on it fairly consistently as well, and that means that the flight will be fairly predictable. And when you spin the ball, you can then create desirable forces to move it around in the air too. So what's more, it also lowers the drag considerably, which means that the ball can fly further. Now, that is for a golf ball, which is spherical. Would the same technology work for wings though? I mean, they have very different shapes and they have very different modes of operation, but could wings benefit from dimples too? If they could, then there are so many different fields that could benefit from that. For example, aircraft to wind turbines to drones to even car rear wings, and the list goes on. There are so many potential methods out there, so many potential technologies out there to use. So to answer whether dimples can positively affect a wing's performance, we're looking at this paper here called, if we scroll up, Passive Flow Field Control Using Dimples for Improved Aerodynamic Flow Over a Wing. It is open access, so you can find it in the link below, and the DOI is here for those who are interested. Now, so on the face of this, it is really weird to think that dimples should work on an airfoil, and let me explain why. So the genesis of this idea is from golf balls, and as we've covered, and they are there to make the flow much more predictable. Well, for wings, we don't really have that problem. I mean, as long as you have flow attached, so you stay below the stall angle attack, then you'll be fine. So maybe there is something else that it does to help to improve a wing's aerodynamics. Let's find out. So to find out, these researchers used computer simulations and CFD in particular to determine how these wings perform. And we can see their wing setup in figure 1 here. Here we go. So just quickly, the wing itself, as shown in the bottom half of this figure, is a NACA 653-218 profile. That means that it has a very thick section and is only slightly cambered. So its thickness is 18%, and that occurs at around 40% down from the leading edge, so about here maybe. And that is very different to many other wings because usually the maximum thickness occurs quite close to the leading edge, like 20% or 25% from the leading edge. But by putting the maximum thickness further downstream, you're making the lowest pressure on the airfoil occur further back. And that then results in there less time for the pressure to recover as you hit the trailing edge. Now, that could pose stall problems, and often it does at low speeds. So this gives us a clue as to maybe how these dimples might affect the wing's performance. This swing in particular has some bad stall characteristics, even at low angle attack, so the dimples might help there. Now, to see if they do, these researchers put dimples in 3 locations, as you can see with these blue circles. They station them at 15% from the leading edge, then 50% from the leading edge, and then 85% from the leading edge, so almost at the trailing edge here. And the potential benefits of these locations is very much stall related, I think. So the reasons why is because of how the wing stalls. So this wing starts to stall from the trailing edge, and then that moves forward with the angle of attack. So when you're at, like, let's say 8 degrees or whatever, there's a little bit of stall occurring at the trailing edge. Then at 10 degrees, it starts to move a bit forward, and then by the time you get to 20 degrees, the entire wing is completely stalled. So by placing these dimples where they are, and in particular, for example, the trailing edge, you're roughening up the surface and introducing more turbulence, and that gives the flow more energy to resist stall. Then at 50% from the leading edge, so these ones here, they too, I think, are strategically placed there because this is around where you get an adverse pressure gradient starting to form. So this is where the pressure starts to rise, and the further towards the trailing edge you go, the more the pressure becomes. So again, these researchers are trying to roughen up this surface to give the flow more energy to resist the stall. And then at the very front, so 15% from the leading edge, which I'm pretty sure the researchers did this because they wanted to try to effectively trip the boundary layer from the very start. So they wanted to introduce all these disturbances into the flow near the wall and then have those grow and finally make the flow near the wall completely turbulent. As a result, the flow over the rest of the wing will hopefully remain attached and turbulent. So those are the placements of the dimples and why I think they put them there. But they also tested different configurations too. So in table 1, we see a list of these configurations. So the first configuration is called C1, let's zoom in a little bit here, C1IDSS. And scroll across, here we go. So this means that they only put inwards dimples on the suction surface. What that means is that these dimples were divots and only on the top surface. So like a golf ball's divots, how they're like chunks out of the surface. That's what these are, as you can see, like in this tiny little graph here. Then the C2IDPS configuration has them only on the bottom, these inward dimples. Then for the third configuration, they had these inwards dimples and on both the top and lower surfaces. So they just designate this C3IDBS. And those are all inwards dimples. Then the next two configurations, as shown here, they follow the exact same process, but now with dimples that pop up. So they are effectively semi-sphere stuck onto the surface. Now this geometry is really interesting to me because not only would I not call these dimples, which doesn't really matter I guess anyway, it's just semantics, but more importantly, I think that these types of dimples are not fundamentally the same as the inwards ones. And that is because these are effectively now semi-spheres, and they're just now vortex generators. In fact, there are countless studies on these exact shapes, and what they do is they create counter-rotating vortices, one on each side, as vortex generators. On the other hand, the dimples that are inwards, so divots, they can produce vortices on the edges like little ones, but they aren't really vortex generators. They're more just about being a cavity that produces somewhat random turbulence. So I'm really interested to see how these two different ones perform and if there's a difference. Another important thing to note is that dimples in general is that these dimples have a diameter of 2% of the chord and they are spaced 3% of the chord away from each other. So you can see in this top figure here. You can see they're pretty closely spaced and they were staggered like row 1, 2, 3 of each one of these locations. Now, the Reynolds number was 250,000, which is prime territory to trip this boundary layer into turbulence. We are definitely in the transitional regime here, and even without dimples, there is a good chance that the boundary layer is already turbulent, but I think that these dimples pretty much guarantee that it will be. Now let's move on to their simulation method. So they used steady state RANs, as they say just here, and which is okay. I mean, they only consider angles of attack between 0 degrees and 12 degrees, so they aren't hitting that postal regime here. As such, they aren't going to be dealing with very unsteady flow, and so I think RANs is generally okay. One really good thing is that they use the KMEG SST terminus model, as I say here, and the reason why this is so important is because this terminus model is far better at transitional flows over an airfoil than any other widespread terminus model used. And I speak from experience because I had to once do that exact same thing for a project where I had an airfoil at a Reynolds number of 225,000 from memory, and then a laminar separation bubble formed over it. So that bubble is so delicate, and even minor changes to really anything in the flow or even the geometry will greatly affect its formation and how it forms and like if it will burst or not. So I tried more terminus models that I can remember or I care to remember, and the KMEG SST one was the only robust one to predict the bubble across different angles of attack. Another decent one that I came across was the Gamma Reynolds Theta model, but it wasn't as good as the KMEG SST one. As for the K Epsilon and its family, and then the basic KMEG one, they weren't even in the same ballpark, so forget about those ones. Now, it's really good that they chose this terminus model. They stand a good chance of getting good results. And just as a quick side note about how this model works, so effectively it combines the K Omega and the K Epsilon terminus models together, and depending on the mesh and the flow, it triggers one or the other. As a result, you can have a much coarser mesh and than you usually would with the K Omega model, but I wouldn't recommend it. I mean, like when you're dealing with flow close to the wall, and when that flow pretty much dominates what happens in the rest of the flow, then you want to resolve that area as much as possible because that's going to change the flow physics. And in this particular case, that flow definitely dominates the flow physics here on this wing, and particularly as you reach the stall angle attack. So you want a finer mesh around the wing. Now in figure 2, we see the domain, and that they simulated the wing in, and it looks really good. So it's not the type of domain I would have picked to use. I would have picked a C inlet domain, so I wouldn't have to then remesh for every angle attack, but rather just change the inlet velocity angle. But nonetheless, in terms of the dimensions of this box, it's good. There won't be much influence from the boundary layer, from the boundaries on this wing performance, which is also good. So one thing to note is that they mounted the wing to the sidewall, as you can see here. Let's zoom in a little bit. Here we go. It's mounted just there. So that means that this wing will act kind of like one with twice the aspect ratio, because of effectively potential flow and that reflective effect on the wall. For meshing, they said that the orthogonality to the cells was above 0.152 and the skewness was below 0.558. Those are both pretty decent values. For those who don't know, the orthogonality of a cell in a mesh refers to, in layman's terms, how slanted the face is between the cells. So for example, if the face is slanted like, for example, a rhombus, then the orthogonality is less than 1. And the worse it goes, the worse the mesh is. Skewness is effectively how squished the cell is. So these two parameters, along with others, are important for a mesh because the worse these values are, the more errors creep in. And as a quick side note, if you want to learn more about CFD and in particular OpenFOAM, which is a very powerful and free CFD software, but hard to learn, then take a course in the link below. Now let's move on to figure 3. We see some pictures of their mesh, and there are really quite a few things I really like about this. Let's zoom in a little bit so we get a better picture of what's going on. Here we go. So in figure 3a, we see that the mesh around the dimples is much finer than the rest of the wing. That's really good because these dimples are now better resolved and the flow physics that comes from them too. So that's a great thing. Then in figure 3b on the right here, we see the boundary layer mesh as given by these layered cells, and that get thinner as you get closer to the surface. And I really like how fine they are too. One really important factor about this boundary layer mesh is what the y plus value comes out to be. Now in equations 7 and 8, which are, where are they? Up, I guess. Here we go, 7 and 8. We see some information about the y plus value, what it is. And just in general terms though, the y plus tells us, based on the velocity of the flow, the density and the wall shear stress, how well resolved the flow very near the wall is. The reason why that is important is because this very near wall flow, we have a lot of important structures forming in the flow that could lead to turbulence. And if you don't pick up these ones, then that will dramatically change the flow and hence the rest of the simulation. Now, depending on the turbulence model, you want to have different values. So the great thing about the Cambic SSD turbulence model, which is what they used here, is it's incredibly robust. So you can have y plus values less than 1 all the way up to 300. But it is advisable to have it less than 1 usually. Here they say that it's good to be less than 3, but it is more common to say 1. Anyway, 3 is still really good, so their y plus value is less than 3, which is nice. So in figure 4, we see the grid independent study. Let's zoom in here. Here we go. So this grid independent study tells us how much the simulation results are affected by the number of cells you have in the mesh. So effectively how fine your mesh is. The finer the mesh is, generally, the more accurate your simulation will be. Now, there will come a point where increasing its fineness doesn't change things very much. Then there will come a point where increasing its fineness doesn't change things very much. And the number of cells you decide to use is really up to you and what you're happy with. Now here in figure 4, the parameter they used as the benchmark to indicate how accurate their simulation was the drag coefficient, as you can see in the y-axis. Now, a really good thing is they increased the number of cells quite a lot that they used. They went from about 4 million up to about 11.5 million. And they found that between the middle fineness, so this middle region here, and the finest meshes, the drag coefficient only changed less than 1%, so like 0.7% or less. So they decided to use the middle finest mesh, which makes a lot of sense. They'll save a lot of time with the simulations and still get pretty much the same result. So one thing to note is that this figure also shows the drag coefficient at different angles of attack. And it's important to note that the changes in the drag coefficient with increasing fineness changed with different angles of attack. So that's important to note because it shows that for a grid-independent study, it's really important to select the worst case scenario. And the authors did a fantastic job here because they looked at so many different angles of attack and they were really thorough. So they managed to do that. So this is probably the best grid-independent study we've seen on the podcast for probably about 8 months, maybe longer, maybe the entire year. Anyway, moving on to figure 5. Let's zoom out a little bit here. too close. There we go. Okay, so we see the validation. And for this one, they are quite thorough with it too. However, this validation CFD is with the Aero M6 wing, which is a little different to the wing that they had in this paper. So this is the wing here that they have. This is the 65-3-218. And the main difference between an Aero M6 wing and this wing is that the M6 one is quite a bit thinner. That shouldn't change things too much, but let's just keep that in mind as we look at this validation. Now, one thing I don't like is that they only plot up to 8 degrees, even though the rest of the study, they look up to even 12 degrees. So I'm not sure why they stopped at 8 degrees. Perhaps the validation data they got from references 41 and 42 only got up to 8 degrees. Anyway, the data they do show aligns very, very well with this validation data. So I think that anything 8 degrees and below, we can really trust. Anyway, above 8 degrees, I'm not too sure about it, especially because you're now hitting the stall regime a little. And from experience, that is usually where wing CFD simulations start to become really, really difficult to do accurately. It breaks down there. So I'm going to say that anything above 8 degrees, we should treat generally as just a general trend and not necessarily as exact values. But below 8 degrees is sweet. So in figure 6, we see the pressure coefficient distribution over the wings. This is again for more validation with CFD compared to experimental data. The validation data is the triangles and the CFD is the solid black lines. And I'm pretty sure this is for 3.06 degrees. Anyway, their CFD is really good. It follows the experiments very well. So I think the CFD method is really good. Let's move on to their results now. So in figure 6, we see the drag coefficient in the top left, the lift coefficient in the top right, and the lift to drag ratio in the bottom left. The squares are for the smooth airfoil with no dimples, and then the other symbols are for the various dimpled airfoils. Now, one thing to note is that the lift coefficient, so the right plot here, let's zoom in a little bit so we can see better. Oh no, here we go. Okay, here we go. So for this lift coefficient one, there's not really much of a difference between these values. I mean, not until 8 degrees is there much of a change. And then at 12 degrees, there's slightly better lift for the C1 IDSS airfoil, which is the airfoil with only inwards dimples on the top surface. Now remember, at this angle attack, 12 degrees is above the validation range that they tested. So I think this difference may or may not actually exist. But for the drag coefficient, which is on the left here, there is definitely a major reduction for pretty much every inward dimple configuration on the top surface. There is like an even 5 or even 7% reduction across the angle attack ranges for the drag. That's insane. I mean, they're even getting this at very low angle attack as well, which is really impressive. Now, the best performing ones are pretty much when you have the inwards dimples on the top surface only. So this C1IDSS one, this circle compared to the triangle. But even when you have them on the bottom too, so the triangle, there's still some major benefits. Now, the outwards dimple ones kind of suck, and I'm not surprised about that because, again, they're effectively vortex generators, and unless you make them micro vortex generators, you're going to get a drag penalty. So that isn't too surprising here. Now, in the lift to drag ratio plot in figure 7, so this one here, we really only have airfoils with the inwards dimples on the top surface giving better values, so the circles and the triangles. And the interesting thing is that in table 4, it shows that, this is for the lift, it shows that the lift coefficient, even with the airfoils with dimples on the top surface, are posting way better lift to drag ratios, and they have worse lift coefficients. So that lift to drag ratio increase is all because the drag coefficient drops. That's like the main thing that's pushing this benefit. So what that means is if you don't put anything on the bottom surface and definitely don't use outwards dimples anywhere, then you're going to get a much better performing airfoil. Now in figure 8, if we scroll down here, we go, we see the streamlines showing what's going on in the dimples. So effectively, the inwards dimples just provide regions of recirculation. You can see all this recirculation here in all these ones. One thing to note is that if you look at the 12 degrees, which is this one here, the bottom right, for 85% from the leading edge, so the one very close to the trailing edge, there is no recirculation here. That is because the wing is now starting to stall, and the flow is separated at this point, so the dimple isn't really effective anymore. Now in figure 9, we see the surface streamlines of the smooth wing, and then in figure 10 we have that for the C1 IDSS wing, which is the airfoil with just inwards dimples on the top surface, which is also the best performing configuration too. The pressure is also given in the color bar. Now something that is interesting, let's zoom out a little bit so we can see both of them. Here we go. So something that is interesting is that as angle attack increases, you can see more and more of the wing has stalled. And you can see that by the horizontal line going across the wing. So as you increase angle attack, that line starts to march forward for both of these ones. And that's the interesting thing, that the dimples that are inwards don't really affect the stall. You get just as much stall without them as with them. At least that is what I'm seeing here. The authors say that the stall is lessened with the dimples, but I don't think that's really the case. And I also don't think that's the case because if that were the case, then the outwards dimples should perform well too, because they are vortex generators. So in my opinion, it's that these wings aren't benefiting in terms of stall. Let me know in the comments though what you think. Instead, what I think the dimples are doing is straightening the flow, particularly around the wingtip. So you can see the wingtip here compared to the wingtip for the dimple ones. So what I want to know then is, if these dimples are straightening the flow near the wingtip, can you get the same drag benefit and the same lift to drag ratio benefit with just putting these dimples at the wingtip? And with that question, we come to the end of this podcast. So the research was done with CFD, and if you want to learn how to do CFD, in particular OpenFOAM, which is a very powerful and free CFD software, but hard to learn, then check out our course and link below. And if you like this podcast, hit the like and subscribe buttons. It helps us out a lot, and we'll see you next one. Peace, amigos.